Hey guys, Miss Gosling here. In this video, you're going to learn about the star life cycle. By the end of the video, you'll be able to describe stellar evolutions for stars off the main sequence. So let's go ahead and get started. So let's go ahead and, before we get into things, discuss your IB understandings, applications, and skills. Your understanding that is the part of this first understanding that is relevant for this subtopic is stellar evolution. Next topic, we're going to discuss the on HR diagrams part, so don't worry about that yet. The applications and skills, and just a reminder, when we see the word describing, that means often both qualitatively and quantitatively. So you are expected to be able to describe the evolution of stars off the main sequence, so what happens to stars when they leave the main sequence. And you're supposed to be able to describe the role of mass in stellar evolution. So let's go ahead and get started. Now, before I get into describing the steps of the star life cycle, I do want to just mention one feature of this presentation, and that is that when you look on many of the slides, you will see words in bold followed by definitions. Please make sure that all of these vocab terms, as well as their definitions, make their way onto your flashcards for this unit. So, with no further ado, let's talk about the beginnings of stars. And before we to get to the beginnings of stars, we really do need to go back to before the star is a star. Before a star becomes a star, it's a nebula. And a nebula is a big collection of dust and ionized gases. In other words, it's a big cloud of the things that stars are made of. Pictured here is an example of a nebula. These are the pillars of creation, which are one of the more famous nebulae that we can see in the sky. Now, that nebula, as we know, is made up of a bunch of different ionized gases. Every single one of those gas molecules has mass. And if there's one thing we know about mass, is that mass attracts other mass to itself. And so the nebula eventually is going to attract in on itself. It's going to condense under the force of gravity and will form a protostar. Now, a protostar looks very similar to a star, but has one important difference, and that is that it is not yet hot enough to begin nuclear fusion. So while it has enough mass to appear to have luminosity in the night sky, it is not currently fusing hydrogen into itself to form helium. Now, eventually, that protostar is going to condense enough that its temperature will heat up enough to begin nuclear fusion. Because remember, nuclear fusion has a really high temperature needed in order to start nuclear fusion, because we have to have our molecules moving very, very, very quickly in order for them to overcome the electrostatic repulsion between their electrons and for their nuclei to overcome the electrostatic repulsion between the protons in their nuclei. So this star is now currently fusing hydrogen into helium, and it has finally joined the main sequence. This is the stage that our sun, pictured here, is currently at. Our sun is currently fusing hydrogen into helium and is a member of the main sequence. Eventually, however, that star is going to run out of hydrogen. When that happens, the core is going to collapse in on itself. The reason that the core collapses in on itself is because we no longer have radiation pressure, yeah? So when my star runs out of hydrogen, here's my star. What I have is I still have that internal gravitational pressure, but my radiation is gone, fusion is no longer happening. And so there is no radiation pressure on the inside to balance out that inward gravitational pressure. As a result, the core collapses, and it's going to collapse in on itself until it gets hot enough to re-begin fusion. At this point, rather than fusing hydrogen into helium, we are now fusing helium into heavier elements. So for example, we are getting carbon and neon and silicon and oxygen and lead within the core of that red giant. Now, this is the core of the red giant. The outer layers of the red giant are going to expand. And as we know, when we see our volume increase, we see our temperature decrease. So the volume and the radius of the star are both going to increase. And what we're going to see is that the outer layers, as we would expect with our gas laws, are going to cool down. Now, at this point in its life, the star is known as a red giant. One example of a red giant that's pretty famous is Betelgeuse, pictured here with the little arrow. Betelgeuse forms one of the shoulders of the constellation Orion, famous for his extremely visible belt, even in places with a lot of light pollution like we have here in Northern Virginia. Now, eventually, we are going to run out of elements that we can fuse together at all. And what's going to happen is eventually these stars are going to start fusing helium into beryllium, and they're going to expand enough and cool down enough that they can no longer sustain nuclear fusion. At this point, they are going to collapse in on themselves. For stars like our sun, this collapse is actually stable. So stars like our sun are going to form a white dwarf and a planetary nebula. So you can see over here in our picture, we have an example of a white dwarf surrounded by a planetary nebula. So a white dwarf is a very small, very dim star, and they are extremely dense. These stars are actually only about the size of planets, and they've lost most of their mass because most of their mass has gone into that planetary nebula because they no longer have the gravitational pull to keep all of the ionized gas and dust that had originally been part of the star locked into the star. Now, one thing that's really important to know about white dwarf stars is that the thing that is preventing the star from continuing to collapse in on itself and get smaller and smaller and smaller and hotter and hotter and hotter is that there's an electron degeneracy pressure within the star that prevents the star from collapsing. Now, electron degeneracy pressure essentially happens when the electrons in the different ions in the star fill the lowest energy states of the stars, of each of the atoms in the star. Now, once that lower energy stage is filled, the other electrons that are left can't fit into that state anymore. So they have to fit into a higher and higher energy state, therefore traveling faster and faster and faster. So these very, very fast electrons create pressure, and that is what I'm talking about when I talk about electron degeneracy pressure. And for stars like the sun, that pressure is enough to stop the star from continuing to collapse. And when I say stars like the sun, I just want to mention I am specifically talking about stars with a mass of 1.4 times the mass of the sun or less. Now, if that star is a little bit heavier than the sun and it has a mass of 1.4 times the mass of the sun or larger, it is not, that electron degeneracy pressure is not going to be strong enough to stop it from continuing to collapse. So the force of gravity is going to be stronger than the electron degeneracy pressure, and it's going to continue to collapse in on itself. And it is going to eventually explode and go supernova. And when that happens, it's going to create a neutron star. Now, at this point, the star has lost most of its mass when it becomes a neutron star. But some stars are still so heavy that they're not stable as a neutron star. So if they have a mass that's less than 2 to 3 times the mass of the sun, they will be stable as a neutron star and they will stay at that state. However, some stars are so heavy that even after they've lost most of their mass, they still have a mass that is 2 to 3 times the mass of the sun. Those stars are too heavy, too massive to be stable as neutron stars. And instead of stopping the collapse when they become neutron stars, they are going to continue to collapse in on themselves and become black holes. So to summarize, there are a few different places where stars can end their lives. So what's going to happen is my star is going to become a red giant and then collapse in on itself and become a white dwarf. This will be the final stable state of the star. It will stay there if its mass is less than 1.4 times the mass of the sun. If, however, as a white dwarf, it would have a mass that is greater than 1.4 times the mass of the sun, the electron degeneracy pressure in the white dwarf is not strong enough to overcome the force of gravity, and it is going to continue, it is going to go straight through that white dwarf stage and continue to collapse in on itself. When that happens, it will go supernova, and it will create a neutron star. So again, if mass is greater than 1.4 times the mass of the sun, we continue collapsing and we have a supernova. From that supernova, we are going to create a neutron star. And if that neutron star has a mass of less than 2 to 3 times the mass of the sun, then again, evolution stops there. However, if the mass of the neutron star is bigger than 2 to 3 times the mass of the sun, it's not going to stay, we're not going to be able to stop at that neutron star state, and instead that star is going to continue to collapse in on itself and form a black hole. So what determines whether a star is stable at a given state or not is what its mass is at that state, not what its mass was on the main sequence. And that's something I want to make sure that I emphasize. Now, before I go forward, I do also just want to mention one fun fact about supernovae. Supernovae are absolutely brilliant. They are these huge, bright explosions in the sky. The last time that a supernova happened was in the early 1600s. It was witnessed by the astronomer Johannes Kepler, and he described it as being brighter than Jupiter, which is one of the brightest objects in our sky. Now, really briefly, I did want to talk about why larger stars go supernova. So, just a reminder, our red giants, pictured on the right, are stars that are fusing elements other than hydrogen because they've run out of hydrogen. So again, our smaller stars expand and cool as hydrogen is fused into beryllium, and when the star collapses in on itself, it forms a white dwarf. For our larger stars, what actually is happening is they are fusing until iron is formed. Then nuclear fusion can't continue without energy input because we can only have we can't fuse anything from iron without additional energy being put in, since our heavier elements are less stable than iron is. So what happens is, when this happens, again, we lose our radiation pressure, just like we do with our smaller stars, and the star is going to, again, collapse in on itself because of gravity. When this happens, the star is going to heat up as the kinetic energy of the particles increase because the volume they take up decreases. This is a gas law reference. And what's going to happen is that the pressure is going to get so high that the star explodes into a supernova. Now, a couple of quick pieces of terminology that I want to make sure enter your notes, enter your brain, enter your flashcards. First, I want to formalize the Chandrasekhar limit. So we already talked about how the maximum mass that a white dwarf star can have is 1.44 times the mass of the sun. This number was discovered by the physicist Subrahmanyan Chandrasekhar, and so we call this value the Chandrasekhar limit. It is the maximum mass that a white dwarf star can have. The other specific piece of terminology I want to make sure enters your vocabulary is the Oppenheimer-Volkoff limit. So this is the other limit that we talked about. This is the maximum mass that a neutron star can have, which is between 2 and 3 solar masses. This limit was discovered was calculated by the physicists Oppenheimer and Volkoff. And what they discovered was if the mass is too heavy, that neutron star will, again, collapse in on itself and become a black hole. And one thing that I want to mention is, unlike the Chandrasekhar limit, the Oppenheimer-Volkoff limit is a range because we aren't 100% sure what the maximum mass a neutron star can have. And the reason for that is we don't know what the equation of state for the inside of a neutron star looks like. Just an FYI, that's a little beyond the scope of the class, so you don't actually need to know this. You just need to know that the Oppenheimer-Volkoff limit is a range, not a specific value. So let's go ahead and do one quick example together. So first, I'm going to ask you all to suggest the conditions that will cause the sun to become a red giant, and then outline why the sun will maintain a constant radius after it becomes a white dwarf. The first question is 3 marks, the second is 1, so make sure for the first question you are making 3 distinct points, and for the last question that you are making 1 distinct point. Go ahead, take a moment, and see if you can solve this question on your own before we go through the mark scheme together. Okay, so let's take a look at the mark scheme. So as you know, that first question was 3 marks. But here, what you might see is that there are, in fact, 5 check marks here. 1, 2, 3, 4, 5. What this means is that there are 5 statements that would be accepted as answers to this question. And if you have 3 of them, you get full credit. So this gives you a little bit of flexibility because, as you might notice, we don't have OWTTE here, other words to that effect. So what that means is you are expected to have this specific language. So they give you a little bit more flexibility with the number of potential things that could answer this question. So while you look at the answer, please pull up a different colored pen, and let's take a look together. So if you wrote that the fusion of hydrogen in the core eventually stops, or that the core contracts, you get one check mark. You only get one check mark even if you said both things. So give yourself a check mark or don't. Next statement, the hydrogen in a layer around the core will begin to fuse. If you said that statement in just about those exact words, check. The sun expands and the surface cools. You have to have both parts of that statement. You get one check for both parts. Helium fusion begins in the core. Again, give yourself a check mark. And the sun becomes more luminous or brighter. Give yourself a check mark. If you mentioned becoming a white dwarf or becoming a neutron star or becoming a black hole, you don't get any credit for that. That is just extra time that you wrote down, or extra things you wrote down that you did not need to write down. So go ahead and give yourself a score out of 3 for question A. And then take a look at the answer for B. So for B, the only thing you need to say was electron degeneracy. If you wrote nothing else, you would still get full credit for this. One thing I want to mention is that you get 0 points if you mention radiation pressure or fusion reactions, because that's not what's happening in a white dwarf star. The other thing I would like to point out is that graders are told to ignore mentions of the Chandrasekhar limit, and the reason for that is that mentioning the Chandrasekhar limit doesn't actually answer this question, because this question is about what makes white dwarfs stable, and the Chandrasekhar limit tells us what makes them unstable. So go ahead and again give yourselves points for this question. Grade yourself and don't be nice about it. Be as honest as you can, so that way you can see for yourself what sort of things you need to make sure you are mentioning that maybe you are forgetting to mention. And we are finally at our takeaways. So first takeaway, evolutionary stages of stars: nebula, protostar, main sequence star, a red giant or supergiant, a white dwarf plus a planetary nebula, to maybe or a neutron star or a black hole. If a star ends as a neutron star or black hole, we don't mention the white dwarf stage. Similarly, if it ends at a black hole, we don't mention the white dwarf or neutron star stages. And the reason for that is those aren't actual stages for that star, because it's not stable there, so it doesn't stop and hang out at that stage at all. It just continues collapsing. Second takeaway, Chandrasekhar limit: maximum mass a white dwarf star can have without going supernova. And the Oppenheimer-Volkoff limit is the maximum mass a neutron star can have without becoming a black hole. So there you have it, guys. I have just thrown a ton of vocabulary at you. Please make sure you take some time to write yourself some flashcards and go through those flashcards as well, just to make sure that you are fully remembering all of these new words that I have just introduced you to today. So best of luck and happy learning.